Okay, so now that we know about the fundamental data types, we're ready to take a look at the arithmetic operators in C++. These are somewhat simpler than they are in Python. We do have both unary and binary, plus and minus. We don't have any exponentiation operator. Instead, what we have is a POW function that computes x to the y. To use POW, you need to include this header CMath. One of the philosophies of C, which C++ somewhat follows, is that small operators do small operations. Exponentiation turns out to be quite expensive compared with addition and multiplication. Consequently, you are required to call a function in order to do it so that it's clear to you that that's an expensive thing to do. The multiplicative operators have higher precedence than addition and subtraction, no surprise. And you can, of course, use parentheses to override or clarify precedence. Association of all of these operators is left to right. There are no surprises going on here on slide 20, so I'm just going to cruise past that. Now, integer division in C++ always truncates towards 0. So integer division is sort of like floor division that we have in Python. 6 divided by 4 as integers gives me a 1, because that's the whole part of the division. Likewise, 1 divided by 3 gives me a 0. Truncation is towards 0, as I said, so minus 7 over 2 gives me a minus 3 in C++ rather than a minus 4. The modulus operator, as you would expect, gives you the remainder after division. However, in C++, this is only defined for integers. You can't use modulus on floating point numbers. Now, anytime you do arithmetic, anytime you use any of the arithmetic operators, there are several steps that always occur in the evaluation of that arithmetic expression. First is what are called the integral promotion. Basically, the idea is to take the small integer data types, bool, char, and short, and automatically promote those to int before the resulting computation is performed. You can see the full gory details of this integral promotion rule in the section on cppreference.com. Now, a Boolean true, when it's used in arithmetic, is promoted to an int value of 1. False becomes 0. A character literal is simply promoted to its corresponding integer value in the ASCII character set. Let me put back up this ASCII character set for a moment. Here we have the ASCII character set. So you can see, for example, that capital A, the capital A character in the ASCII character set, has an integer value, a decimal value of 65. Little a has a decimal value, sorry about that, little a has a decimal value of 97, and so forth. The space character, that is quote single space quote, has a decimal value, an integer value of 32. The null character is the character whose value is 0. And we usually represent the null character in code with quote \0 quote. The character 0, on the other hand, has the decimal integer value of 48. Let's flip back to our ASCII chart to confirm that. Okay, so here is the so-called null character whose decimal value is 0. The 0 character, on the other hand, in the ASCII character set, has a decimal value of 48. So it's very important to keep those two distinct from each other. Okay, so the space character, as I said, is promoted to an int 32. The new line character, which is represented with \n in C++, just like in Python, or perhaps I should say the reverse. The new line in Python is represented as \n, just like it is in C, C++, and Java. And I pointed out that capital A has an integer value of 65, little a has an integer value of 97 in the ASCII character set. So these promotions just occur automatically. You're not warned about this. You're not asked about this. It just happens. Consequently, if I write an arithmetic expression such as this one, true plus quote little a quote minus 5, this is evaluated from left to right. So true plus little a. First of all, the integral promotions occur first. So true is promoted to int 1. Little a is promoted to int 97. So we get 98, and then we subtract the int 5, and we end up with an int value of 93. All right? False, here we're doing multiplication involving two bool values. False is promoted to 0. True is promoted to 1. And of course, the product is an int value of 0. Now, the character 0 times the character 2, well, if we look up in the ASCII character set, we already saw that character 0 has a value of 48 in ASCII. Character 2 is 2 characters later. It has an integer value of 50. And the product of character 0 times character 2 is treated as the int 48 times the int 50, and that's 2040. True plus true is not true. True plus true is treated as 1 plus 1 is equal to 2. So these so-called integral promotions occur on any of the so-called integer subtypes. The bool, char, and short are all promoted to int. Then, if there are also larger kinds of integers, such as long ints or long ints, or if there are floating point types involved, float, double, or long double, the so-called usual arithmetic conversions are brought into play, basically converting the value of the little data type into the bigger data type. All right, so if you add an int and a double, the int is converted to double first, and the result is double. If you multiply a char by a long, the char is first promoted to int because you're doing arithmetic operations on a char. Then the int is multiplied by a long, the int is converted to long, and the result is long. Okay, so to find out all these gory details, you can look in the standards documentation for usual arithmetic conversions, and you'll find all of these gory details. Now, we are only looking at a restricted set of data types, namely char, bool, int, unsigned, double, and void, as I mentioned, as well as null pointer. So when we use these things in arithmetic, char and bool are going to be promoted to int. Now, int and unsigned are the same size in memory, and consequently, if you combine an int and an unsigned, the unsigned is considered to be the quote bigger unquote type, and the int is therefore converted to unsigned. On the other hand, if double is involved, then both operands are converted to double before the arithmetic operation is performed. Now, the integral promotions and the usual arithmetic conversions, it's important to understand, are performed one subexpression at a time, following the precedence and associativity rules for the values involved. We were careful, and I didn't emphasize this, but we were careful when we wrote our Celsius to Fahrenheit conversion example to perform the double precision subtraction first, which gives us a double precision result. Now that double precision result times an int causes the 5 to be converted to double. The result is double, which in turn is then divided by 9. So division by 9 is the last thing that happens, and we get a double precision result. All right? So in other words, step by step, because of the parentheses, the subtraction of one double from another occurs first, and we get a double value of 46.0. Then that value, which is a double, is multiplied by an int. Therefore, the int is converted to a double 5.0, and the result is the double 230.0. Now, that result, 230.0 as a double, is then divided by an int. The int is converted to floating point, namely double precision 9.0, And 230.0 divided by 9.0, as we discovered, was 25.555, to the extent that that can be stored in a 64 representation as a double. Now, if you change around the order of this computation, for example, if you do the division before you do the multiplication by the difference, you're going to end up with the wrong result. All right, so here, because of the parentheses, this subtraction is done with a double minus a double, and so we have a double there. But then we have int divided by int times double. And remember that division and multiplication are evaluated from left to right. So 5 divided by 9 occurs before the multiplication, and 5 divided by 9 gives me an integer value of 0. All right, int divided by int gives you the whole number part as an int. So 5 over 9 is 0. 0 times anything is 0. So we end up with a double precision 0.0 as the result of this thing. Similarly, if we just wanted to use some parentheses to try to clarify the parts of our computation, we're saying, all right, let's subtract freezing from the Fahrenheit temperature, and then let's multiply that by 5/9. Well, unfortunately, this 5/9 here, again, is 0. And so we end up with a result of 0. You can change the order of things and do your division part first, as long as either the 5 or the 9 or both is forced to be a floating point value. One way of doing that is to simply put a decimal point after the 5 or after the 9. All right, so here again, 5 over 9 is evaluated first, but this time that's a double precision result of 0.55555 and so forth. And that can then be successfully multiplied by the result of this double subtraction to yield a double value. Okay, so these rules about integral promotion and usual arithmetic conversion are annoying but vitally important. Always, whenever you write an arithmetic expression, you have to think on a piece-by-piece basis of what the data types of your values are and how those data types are being converted during the computation. If you fail to do that, you're going to end up with problems. Okay, now we would like to be able to carry these values that we're computing around in variables, and in a function, or for that matter, any block of code contained between curly brace characters, we can declare and use what are called local automatic variables. Now, local means that the variables are only usable within that block or within that function and are invisible outside of that block or function. Automatic means that the variable is automatically created in a region of memory called the stack when the function is called or when the block is entered, and also that storage is automatically deallocated from the stack when we leave the function, that is, when we return from the function or leave the block. Now, we can return from a function by using a return statement, or if there's no return statement, we can return from a function or leave a code block by hitting the curly brace at the bottom of the function or the code block. Now, variables in C++ may be uninitialized. Here on slide 28, we have a main function, and within the body of main, that is within the block of the main function, the first statement here is the declaration, so-called, of a local variable called ft1, which contains a double value, but this is uninitialized, so the value of ft1 at this point is undefined. It is whatever garbage happens to be sitting around on the stack at the point where that variable ft1 is allocated. Unlike Python, you must declare the data type for a variable before you can use that variable, and the data type of that variable cannot change throughout the variable's existence. So in Python, we could say, x gets 12, and x is referring to an int. We could then say x gets 2.7, and x is referring to a float. We could say x gets hello, and x is referring to a stir. Here, in this main function, ft1 is a double variable. It occupies a certain amount of memory on the stack, and ft1 can only ever contain a double value. Whatever pattern of 64 bits is in ft1, that is the value of that variable ft1 at a certain moment in time while this main function is running. It's a good idea to initialize a variable whenever you can. In fact, it's a concept or a standard convention in object-oriented programming that you should not have any object existing in some undefined state. And this applies to ordinary low-level objects, low-level variables, just like higher-level objects. All right, so here, ft1, we're sort of violating this convention. ft1 is an object whose data type is double, but whose state is undefined, whose value is undefined. In these next three statements, we're declaring that ft2 is a double variable, a double object, and ft2's initial value is 78.0. This equal sign is pretty common in declarations and initializations of variables. It's a style of initialization that dates way back to the C language, all the way back to the mid-1970s or so. In C++, we can also, instead of using an equal sign, we can use parentheses around the value that we want to initialize the variable with. In this case, ft3 is a double variable initialized with 78.0. This is a constructor style of initialization that was introduced with C++. And more recently, C++ 11 introduced the idea of using curly braces to contain the initial value of a variable. Okay, so here on slide 28, these four variables, these four objects, ft1, ft2, ft3, ft4, are local to the body of main. They're local to this block of statements contained between the curly braces, and they will only exist so long as the main function is executing. As soon as the main function returns, then these variables are deallocated from the stack. Now, since main is the initial function, of course, that also means that the program itself is over, and so all of the information on the stack is going to be deallocated at that point anyway. Well, rather than hard coding these values 78.0 directly in our source code, it would be more flexible to be able to read these things in from a user, let's say. We can use cin, which is sort of the opposite of cout. Cin is the standard input stream object to get data from the keyboard using this double greater than symbol operator. And this is called either the get from or the extract operator. Here's an example on slide 30 where I have declared and initialized a double variable named ftemp in my main function. Then I'm using cout to display a prompt to the user, enter Fahrenheit temperature. Notice that this enter Fahrenheit temperature string does not have a \n at the end of it. Consequently, after this string, enter Fahrenheit temperature : space, has been displayed, the prompt is just going to sit after that space waiting for the user to type some input. Now, if what the user types as input can be treated as a floating point number, then we will extract from cin the characters for that floating point number, and we will put the corresponding actual floating point number into the variable ftemp. Then we'll be able to display using cout that ftemp, whatever that is, degrees Fahrenheit is. We'll compute and display the value of this computation, degrees Celsius. All right, well, let's give this thing a try. I'm going to switch to my Ubuntu screen. All right, so I've switched to my Ubuntu terminal, and here I am in the lec1 directory where my lecture 1 related files are stored. I have not created this F2C3 file yet, so let me do that. In fact, let me put this program up on the other slide. So I'll put slide 30 over here and then switch back to my prompt. All right, so here I have hello and its various relatives, and I'm going to create f2c3.cpp and type it in. And I will start talking again after I've gotten this thing typed in. Okay, so I have completed typing in this code. I have started out with a comment saying the name of the file, then I've included iostream so that I can do input and output using cout and cin. I just noticed that I misspelled cin, so let me fix that. All right. I've done my using namespace standard, so I don't have to use std::: in front of cout and cin each time. My main function declares and initializes ftemp as a double variable initialized with 0.0. Then I display a prompt to the user. I wait for the user to type some input, and if that input, that sequence of characters as the input, is a valid representation of a floating point number, then from cin we'll extract those characters and create that valid floating point number notation in a 64-bit pattern. And then finally we'll use cout here to display the temperature degrees Fahrenheit is, and then the corresponding Celsius temperature, followed by the string degrees Celsius. Main will return a 0. When that happens, this f_temp variable is removed from the stack, and this value of 0 indicating success is passed back to the system. Let me compile and run this thing now. Right, I'm going to save my file by saying :wq. WQ means write and quit. All right, so here's my file. And I'm going to say g++-o f2c3, the program f2c3.cpp. It's done, and I'll run it. Enter Fahrenheit temperature. Well, let's try some things. If I say 32.0, that had better be 0 degrees Celsius. 32.0 Fahrenheit is freezing, so yes, 32 degrees Fahrenheit is 0 degrees Celsius. Let me run it again. Let me type 212. Now that's boiling, so that should be 100 Celsius, and it is. Let me run that again and type in some pleasant temperature. Now, if I type 72, although I've typed just 2 digits, the logic for the cin extract is smart enough to realize that 72 can be stored in a double precision variable. And so that will work fine, and the value 72.0 will be stored into ftemp, and the computation will be done. And I discover, okay, 72 degrees Fahrenheit is 22.2222 Celsius. Now, the output here of a floating point value by default is 6 total digits of precision, even though internally within the machine, that ftemp variable has got at least 14 digits of precision stored. It's simply that by default, when I display a double precision value to cout, I get a total of 6 digits displayed by default. I can ask for more or I can ask for less. Okay, so there's our F2C3 program. Now, users, it turns out, make every conceivable mistake under the sun. If I run my program again and I ask the user to enter a Fahrenheit temperature, a very inexperienced user might say, 53. Well, that makes sense to me. That makes sense to a human being who knows English, that means 53 degrees. But the get from operator, the extract operator, is not nearly clever enough to figure that out. And so what happens is nothing gets read in. The ftemp variable simply contains the 0 value that it was originally initialized with, and I get told that 0 degrees Fahrenheit is minus 17.7778. Okay, so because users make so many mistakes, this is the only time in the entire course that we're going to show you this get from operator. It's very difficult to detect the many, many different ways that a user might make a mistake using the cin get from operator. So we're going to abandon that almost immediately. All right, here on slide 31 are a few example runs similar to what I just did. And that is the end of week 1, lecture 2.